All right, section 23.7, the Clasien condensation. First, a look at the general reaction for the Clasien condensation. We're going to look at the condensation of two esters. For simplicity, I'm simply going to call this one a methyl ester. And in fact, we need two of these. We need a base that matches the ester component. So in this case, this is going to be methoxide. And what we get as a product there's the components of one of my esters, and there's the other. So the new bond that we've made is right here. And so what we make is a beta keto ester. All right, so let's look at one of these specifically. If we take this ethyl propanoate, of course now we want to choose the correct base, so ethoxide is what we need here. We produce this specific beta keto ester, where the components of the starting material 1, 2, 3, 1, 2, 3. There's one ester. We make the new bond between the alpha position and the carbonyl, and then we have 1, 2, 3. So these are the basics for the Clasien condensation. We now want to look at the mechanism, because it's very important that you be able to recognize the driving force for this reaction and explain it, because it's going to impact lots of chemistry. Not only the chemistry we look at for this class, but a lot of biological chemistry. So we start here with our compound that has alpha hydrogens that are acidic. So I'm going to just use the simplest acetate here. We will have ethoxide, anion, and that's a base. We're looking for the acid. The acidic position is the alpha position. We deprotonate that, and that bond swings up. Now, ethoxide could also attack the carbonyl, create a tetrahedral intermediate in exchange. And all of that is, of course, going on. That's why it's important that we match the base with the alcoholic portion. We won't send it to AA or anything, but the alcoholic portion of the ester. So we deprotonate. This, of course, is a reversible process. Oops. Let me make this the ester enolate of 1. Now, here we're going to have this react with another molecule of the starting material ester. Now notice we did a reaction between a base and an acid in the first step. This creates a nucleophile that will react with an electrophile. So let's follow that along here as we go. Now, again, starting at the place of highest electron density, that lone pair is going to swing down to reform the pi bond. The double bond will be the nucleophilic proportion connecting to the alpha position. We attack the carbonyl carbon, and that, of course, will swing up, producing an intermediate. What kind of intermediate? Let me draw. There's my new tetrahedral carbon. Now, this compound will displace the leaving group, in this case ethoxide. Now, we don't normally have such strongly basic leaving groups, but remember we're under basic conditions, so we can have a basic leaving group. This, again, is an equilibrium process. When this has occurred, we produce what appears to be the product, but we're not done. So we have the ethoxide there. Of course, this has protons that are acidic. Okay, so all of these have been reversible. Do you remember the pKa's? Ethanol is about 16, and this beta-keto ester is approximately 11. So the equilibrium here will be approximately 10 to the 5th. And for synthetic purposes, that's essentially an irreversible step. So the ethoxide deprotonates that acidic hydrogen that is alpha to the ester and alpha to the ketone. This produces an enolate, effectively an irreversible reaction that shifts this equilibrium and all of these intermediates over to give us a good yield of product. And then you'll see, I should have put this up here explicitly, but 1 is the base, and then 2 is acid. So 1 is the base, 2 is an acidic workup, and that's because the way that we get the final product here is we can add acid to these reactions, and of course now we can protonate Okay, so the final step, the addition of acid in the workup, produces the product. Now, of course, we know that this is in equilibrium with its enol isomer hydrogen bond there, and depending on the exact details of the structure, we get a significant quantity of the enol. So those are the basic features of the Clasien condensation. It's very important that you recognize this irreversible step in this mechanism as well.